Okay, cool. So let's get on with this. Now, last lesson the last couple of lessons we've been talking about a few different things that the derivative tells us. So let's just quickly do a recap of that again. So when we had our first derivative, we find our first derivative. So f dash of x, like we normally do when we differentiate stuff, and we have three conditions on our first derivative. Table over here, what's the first condition that we can have on our first derivative? If it is
greater than 0.
and greater than 0, what does that mean for if we were graphing a function based on that? Increasing. So if our first derivative is greater than 0 for a particular region, it means that the graph is increasing. It's going from bottom left to top right. So it's increasing. What's the second one? Decreasing. It's decreasing. So if it's decreasing, what's the condition on our first derivative? It is less than 0. And so here our graph will look something like this. Decreasing. And the final one was equal to 0. This is not on any page. This is just a summary of the stuff we've covered over the last couple of lessons. I can go through that with both of you, and the videos will be up shortly. The final one is 0, and that is a...
horizontal point.
No, that's a particular version of stationary point. So a stationary point is any point where the graph at that one particular point has a horizontal tangent. And so there was a few different types of this. So we talked about a few different types of stationary points again. So what's one of our types of stationary points? Local what?
Local minimum.
Local minimum, which looks like a U, and it's a bottom point of our U. We have a local maximum, which is the upside down version.
And the horizontal point.
And excellent. And the last one is our horizontal point of inflection, which looks like a weird S shape. So it's kind of like that, or in the other direction like that. We talked about our few turning points. And then we also started talking about our second derivative. So second derivative, we differentiate once and then we differentiate again. And there was kind of two conditions on this one this time. What's our first condition on our second derivative? If it's greater than 0, what does that mean? It's C word. What was that C word we talked about yesterday? Concave? Up. So here it's concave up. So if our second derivative is greater than 0, it means that the shape at that point is upwards. It's a smiley face. The other one was if it's less than 0, which means it is concave down. Excellent. So here, it's a frowny face. So we went through this yesterday and applying it. We got halfway through a question on page 14. We got halfway through this question. So let's just quickly go through the steps that we did here. What we did, the first thing that we did was we differentiated our original function and we got our first derivative here. Then,
so what was the second point?
Which was the second point?
For the second derivative?
Concave down, less than 0. So that's what we did over the last couple of lessons. So if you remember from yesterday, when we were trying to, what we did was we were finding the stationary points and determining the nature. So if you ever see that question, you just want to solve the first derivative. And from there's a few ways you could do it. The way that we were going through is using our second derivative to tell us if it's a turning maximum or a minimum, a local maximum, local minimum. So just remember, if we have a second derivative is greater than 0 and a stationary point, so if we have a concave up graph and we have a stationary point, is that a local minimum or local maximum? Minimum, because it is at the bottom of our concave up section. So that is a local min. It's our stationary point. F dash x is equal to 0 means we have a local min. If it's concave down, what do we have? Local max, because here, top point, so this f dash x is equal to 0 means we have a local maximum.
Maximum sadness.
And maximum sadness, minimum happiness. We're pitting ourselves within two very sad points. Okay, so what we got halfway through this question and we determined the nature of the stationary point. So we solved our first derivative and we subdomed those points into our second derivative, and that told us we had a local minimum and we also had a point of inflection. Now the final part that we didn't get up to was to sketch the curve, and we actually drew up this table of values to help us sketch it. So let's just get through sketching it and we'll go through another example. So here, on my graph, I have a few things that I can put on. So what's the first thing? What are the 2 points I can put on my graph from my first derivative? We found our 2 stationary points. So we had 0, 0, which is over here. What's the other point that we have on our graph from our stationary points? 3 minus 27. So I'm going to have a point here at 3 minus 27. So we've got our 2 points here, 0, 0, and 3 minus 27. Now we also found out that 0 was a horizontal point of inflection, and so here it's going to look something like this. We're going down towards 0. It's a horizontal point of inflection. Goes down to 3 negative 27. Now 3 negative 27 was a local minimum, so we're going to go from there and go back up to here. That. Now we should also find our second x-intercept, which I believe should be at 4. There's also another point that I can put on my graph that we found from our second derivative. What was this other point that we found? What do we find from, what's it called? Our point, what's it called? From the second part of this question. Yeah, so 2 minus 16 would be somewhere around here. So here we've got 2 negative 16. Now, what does that point actually refer to? Well, if you have a look at the graph, on the left of 2 minus 16, what's the concavity of the graph at this point here? Is it concave up or is it concave down? Down. It's a frowning face. So here we've got a concave down section. How about to the right of 2 negative 16? It's concave up. It's starting to become a smiley face again. So here, this is a point of inflection. This is our point of inflection. That's another point of inflection. Now, as you notice, is it a horizontal point of inflection? Is the tangent horizontal at that point? No. I'm just asking, is the tangent at that point horizontal? No. Notice here, if I drew a tangent at this point, it would look something like this. It's like a slanted line. So this is not a horizontal point of inflection. It's just a regular point of inflection. We do have a horizontal point of inflection. Where's our horizontal point of inflection on this graph? Give me a coordinate. 0, 0?
That one and the...
No. It's just 0. 0, 0 is our horizontal point of inflection. Because the other one is a local minimum. That's not a horizontal point of inflection. So here, this point at 0, 0 is our other point of inflection. Because notice on the right-hand side, we've got concave down. How about the left-hand side? What concavity is this side? A concave up. So it goes from concave up to concave down. Points of inflection just mean you're going from concave up to concave down or vice versa.
Concave up, concave down.
That's what we did last lesson. So let's turn over the page and we'll have a go through this next question. Example 12. So this is example 12 on page 15. So can everyone flip to that page for me, please? We're going to be going through this example. Okay. So have a look at this one. For what values of b, it's a graph of the quartic. So they give you this function, concave down at the point x is equal to 2. Okay, so we want to sub in x is equal to 2 eventually, but what are we checking for? What is the condition? We need it to be what?
Concave down.
We need concave down. How do we get something to be concave down? What's the algebraic definition of something to be concave down? Something is negative. What is it? What's less than 0? F double dash x.
Oh, yeah.
When you are checking for concavity. So if you ever see the word concavity or concave, we are checking for our second derivative. We are checking the second derivative. If you're looking at the tangent or stationary points, what are we looking for? Are we looking for the first derivative? And this was the thing that I showed over here last lesson. If we want to sub in x values if we want to look for y values, we need to sub in x values into the original function. If we're looking for the gradient of our tangent, we sub into our f dash, our first derivative. If we want to find the concavity, we need to sub into our second derivative. And we don't worry about derivatives after that. Okay, so let's go through this example. How do we find the second derivative? How do we find the second derivative? Differentiate twice. We differentiate once, we differentiate twice. So let's differentiate this function for a few times. So we've got x to the power 4 minus bx cubed plus 5x squared plus 6x minus 8. Let's differentiate that once. Ujun, what will I get when I differentiate this once? 4x cubed. 3bx squared. Excellent. Plus 10x plus 6. Excellent. So that's my first derivative. Now that I've done that, I'm going to differentiate again to get the second derivative. So let's differentiate that again. What do I get for my second derivative? 12x squared. 6bx plus 10. Excellent. Now I need this to be... Oh, excellent. Okay, so we don't need to factorize it. When do we need this to be... so we want to have f double dash x is equal... Actually, we don't want that. We want this to be less than 0, but what point?
So,
Yeah.
how did you get 6bx?
Because I did bring the 2 down.
But that's not a b, that's a 36.
That's a b.
Oh my god.
Have a look at the... Guys, you have the question in front of you. You can read the question. You can see that is a b.
So, you're right.
How do you want me to write b? Okay, b, 6. I'm hoping you can tell there's a difference in my b's and 6's.
It looks like a 36.
I'm angry. Okay, we want to have the second derivative is less than 0, but what point? We want it less than 0 at 2. So here I'm actually going to be solving for f double dash 2 is less than 0. So what can I do with this equation that I have? I can sub 2 in. Okay, so I'm going to sub 2 in. What do I get if I sub 2 in?
12.
58 minus 48.
Jumped a few steps, Khan, but yes, I think that is correct. So 12 times
2.
squared. What's 2 squared? 4. So if I do 12 times 4, it's 48 minus 12b, because I have that 2 in there, so this becomes 12b plus 10 is less than 0. Okay, cool. What can I start to do now to make this easier? Khan, what did you do? Huh?
Move the numbers to the other side.
Move. Gosh, too many. I asked Khan. Gosh, damn it. Khan, what are you saying?
Jeez.
Okay, cool. So, as Prakruti and Khan said, we're going to move all the numbers to the other side. So here, I'm going to have minus 12b is less than what? Minus 58. Okay, cool. Minus 58. Now, if you remember, when we talked about inequalities, what would be the next step that we need to do if we were solving this inequality? Divide by what? We need to divide by minus 12, right? But if you divide by a negative number in an inequality, what happens? It changes to... It flips the other way. So here, this is going to be b is greater than negative 58 over negative 12, which gives us what? 26 over 9?
Yeah. You can simplify it.
You mean 29 over 6 and not 26 over 9? Come on, Ujin. If you're going to cheat, at least cheat properly. It's literally right here. Come on, Ujin, learn to read. There we go.
Next one.
Next. Are we cool with this question? So if you ever see in the question concave, concave means you need to do the second derivative. Concave is second derivative. If they ask you about the gradient of the tangent or the gradient at a particular point or horizontal tangent, what derivative are we looking at? First derivative. If we're looking for y values, what are we subbing into? The original function. That's it. There we go. Okay. This is from the 2013 HSC paper. We have a cubic here. We want to find and has a point of inflection at x is equal to p. What does it mean for something to have a point of inflection? What does it mean for our second derivative? F double dash is... It changes concavity. In particular, it has to be equal to 0. Now, I said something about like either side of this point, it needs to be greater than 0, and then on the other side, it needs to be less than 0. But for now, we're just going to we want to solve this particular equation. F double dash x is equal to 0.
What?
So,
Equal to 0?
yes, at a particular point, at x is equal to p.
Differentiate.
We're going to differentiate. Excellent. Let's differentiate once. What do I get when I differentiate this equation, this quartic, or this cubic once?
3ax squared plus 2bx plus c.
Excellent. What do I get when I differentiate again at front table?
Would it be c plus 1? Or do we...
No. Does D have anything related to it? Oh,
It's gone.
it's gone. So it'd be C times 1, not C plus 1.
Yeah, okay.
Yeah? Okay. TJ, can you help me differentiate again so I get my second derivative?
6ax
Excellent.
plus 2b.
Excellent. Now we want to solve when this is equal to 0 at what condition on x?
Equals to 0.
X is equal to 0.
Yeah.
No.
No.
X is equal to what?
P.
P. Excellent. Here, notice we've got x is equal to P. Ooh, that's...
P is equal to minus.
So we want to show in the end that P is equal to this guy here.
Do we just sub?
So we're going to sub in P. So here, if I sub in P, what do I get? Sub x is equal to P. So what will I get?
So 6AP plus 2B.
And what's the condition for it to be a point of inflection? It needs to be equal to 0. Okay, how do I start solving for this guy?
Now you put the P is equal to...
Divide both sides by 6a.
Divide everything by 6a. Okay, we can go 6 P plus 2b over 6a is equal to 0. And then what now?
Move the 2b over 6a.
And what will I get?
Negative 2b over 6a.
Can I do anything to this?
You can
Simplify.
Simplify. What can I cancel out?
The 2 and the 6.
2 and 6, and I get 3 here. And then, so this becomes negative.
b over 3a.
Oh, is that what we wanted to prove? We did it. We did it.
That's it?
That's it. So if they ask you to show that something is a point of inflection, you just want to show that f double dash of x at that point is equal to 0. Now, if you remember from last lesson, if it's a point of inflection, it means that we have second derivative x is equal to 0, but the other way is not true. So we cannot just, by saying f double dash x is equal to 0, assume that it's a point of inflection. This is not true. But for this question, we're just trying to prove that it is. That works out fine. Okay, cool. Is everyone good with that? Okie dokie. Let's flip the page and do one more question. Oh, this is fun. Okay. Using the following information, sketch the graph of y is equal to x, or y is equal to f of x. So, here we have a few dot points for different conditions that we have on a function. And so, we need to actually go through what this means. So, let's go through each one of these parts. And that thing that I said earlier about f of x, f dash x, and so on will probably be quite helpful for us here. Okay, so I'm going to draw my axes. Okay, let's have a look at this first dot point. F of 0 is equal to 0. What does that mean? I can put on my graph. Origin. So this means when I have x is equal to 0, which is this guy over here, I have y is equal to 0. And so this gives me a point. So this tells me that I have a point on my graph 0, 0. Is everyone cool with that? Okay, so let's put that point on my graph. I'm going to do my graph in. Would someone like to pick a color? Galaxy. Oh, Lord. We're doing this graph in Galaxy now. So I have a dot at my origin. Excellent. So that's its first dot point. I've ticked that off. I can tick off that one. Okay, second dot point. F dash x is greater than 0 for all x. What does that mean my graph is happening? F dash x is greater than 0. What does that mean? Increasing. So that means my graph is increasing for all of x. So the whole time, you can't draw anything yet because we don't know other points yet, but the whole time it's going to be increasing. It's going to go from bottom left to top right for the whole graph. So we're going to have an increasing graph. Okay, next one. Next dot point. And I think these next three actually combine together quite well. F double dash x, oh, F double dash 0 is equal to 0. What does it mean for at x is equal to 0? Is it a stationary point? Point of what? This means that we have a point of inflection. So just remember, if the first derivative is equal to 0, that means we have a stationary point. If the second derivative is equal to 0, that might mean POI. Because what else do we need to check? What's the condition for something to be a point of inflection? And this is where we drew the cubic. If you remember,
If it's equal to 0,
so this was a quartic, and here at this point we got that f double dash x is equal to 0. But did we say that this point at the bottom was a point of inflection? No. What do we need to have? What do we need on the left hand side? What's the condition of our what's the concavity on the left hand side for this one? F double dash x is What was that, Khan? Sorry, I can't hear. It is not increasing. What do we know? Have a look at the shape of that. What's a concavity on the left-hand side? It's concave up. Well, okay, so concave is about the general shape. Is it smiley face?
Concave down, it's going up.
It's not concave down. Concave down is this.
I mean, it's going down.
Yeah? Excellent. So that's regarding the first derivative, right? The first derivative is this part here is less than 0 and this part here is greater than 0. That's our first derivative. We're looking at the second derivative. And we're looking for concavity. So we're just looking at the shape. So on the left-hand side, is it concave up or down? Down? Up. So this side here is concave up. Notice here, it's concave up. So that means our second derivative, is it positive or negative?
Positive.
Positive. How about on the right-hand side? Is it concave up or down?
Positive.
It's positive because it's concave
Up.
up as well. So this point here, this point at the bottom, this point here is not a point of inflection. Because notice on both sides, we have concave up, concave up.
Isn't it a local minimum?
It's a local minimum for this one. But this is not a point of inflection despite the fact that we've shown that f double dash x is equal to 0. Does everyone see that?
Okay.
So for a point of inflection, we do need to have this condition that f double dash x is equal to 0. But in order for this to be a point of inflection, we need one side to be concave up and one side to be concave down. So we need a change in concavity. If it was like this, let me try that with a different color actually. If it looked like this though,
That's the point
No, it
of
was a
inflection.
parabola. Because you
oh, that's not the great. This is not the shape. I'm just drawing an example.
Oh, okay.
So
That's a point of inflection.
that's a point of inflection. Why is it a point of inflection? What's the concavity on the left-hand side of my blue graph?
Going negative.
Down, or negative. Second derivative is negative, and then on the other side it's up. So have a look at my other conditions. So let's have a look at this next. So this is POI question mark.
All students having sibling photos, please go to the hall at the end of period 2.
Okay, have a look at this next condition. F double dash x is greater than 0 when x is less than 0. Okay, let's talk about this. What does f double dash x greater than 0 mean? It's concave up. It's concave up for when x is less than 0. So that means x is less than 0. So what this means is anything to the left of my y-axis, this whole region is concave up. like that. Kind of looks like that. How about on the right hand side? When x is greater than 0, what's f double dash is less than 0? It is concave down. So on my right hand side is concave down. So if I add all this together, what the graph would look like is something like this. Does it tell us about any stationary points? Are there any stationary points? No. Because the whole graph is, for every single point, what do we know about our first derivative? It's increasing. The whole graph is increasing. So what this should look like is something like this. So it's increasing, but on this side it's concave down, concave up, and then suddenly here we hit 0, we have a point of inflection, and suddenly it becomes concave down. So concave up on the left hand side, and then concave down. So that's how this graph should, I think, look like in the end. It took me like 2 attempts here. I drew it wrong the first time as well, so don't worry. So here, let's talk about the things that we've had added here. The whole time, the graph is increasing. There's no point where the graph is decreasing. So every time it's increasing. If you have a look at the left-hand side, what's the concavity on this side here? Concave what? Is it concave up or down? Up. It looks like a smiley face. How about on this side? It's concave down. And in the middle, we've got this POI. It's not HPOI, it's just a POI. There we go. Okay, cool. Huh? Horizontal. Okay, so that's that. Now, we'll keep it here for now. I see you guys next week on Monday, period 1. For homework, I believe there's some questions in question 5.03 and 5.04. Can you have a go at the questions in 5.03? Can you just do every second one for me, please? 5.03. William and Ujin, so I'll post up the videos up shortly. I am free on Monday